Alright, so hey there, in this video I'm going to show you how to create the page turning video. So if you're trying to create your own with your own book and running the same code, you can do that. And then we're going to use Python to detect pages, the actual page turns, and then find sort of the best picture in between those page turns that we can extract from the video, because that's what we'll want to send to OCR to get the text off of it. So we don't want anything blurry or not, and I'll sort of show you how we can do that using the Python libraries mentioned here. Here is the video within the video. I'm going to show you what I did here. So notice this is me just using a kitchen table, putting the book on the chair beneath it. I tried to avoid all sort of shadows. You don't see many shadows in here with the lighting above me. And I'm just taking a snippet out. So I'll play that again for you here. And the camera is fixed, and it's just me turning the page. So it's not wobbling, it's not on the same surface. And because of that, it'll make our job a little easier in deciding which picture is the best picture to use. Now that I showed you how to get the video, let's move on with the notebook. So here's our standard imports at the top. CV2, that's OpenCV, that's computer vision in Python. Very, very widely used package. Pandas, you've probably seen that before, data manipulation. Matplotlib will help us with plotting the images and sort of visualizing what we're doing so we can help our algorithm. And then NumPy is going to be very helpful for numerical operations to create our algorithms. And here we go. We're going to load in our video, and video is composed of frames, different images, and sequence played looks like motion. That's a video. Next up, it's always good with images or neural networks, anything that uses like big tensors and matrices, to look at the shape of things. So I'm just sort of outputting what are the frames, what does that look like? And we can see that there's this 338, then we see 3840 and 2160 and 3. So just from sort of knowing, this is close to, I believe it's almost like 4K, but that's my resolution of my screens with the video too. So it is 3840 wide on my camera, and then 2160 high. We need to fix that here. 2160 is the height. Actually, no, it's the other way. I thought I messed it up, but I messed it up the other way. Here we go. It's the height, 2160 is the width. Yes, there we go. So we've got 338 as the counter frames. The only other thing to mention, the color. That's because red, green, and blue can all sort of work together to create every color your eye can see. So that's what this 3 is here. So sort of process of elimination, 338 has to be the count of the frames, since this is pretty clearly a resolution value of the images. So let me just show you what one of the images looks like. It's the ImShow command. It shows us a book. We can't see much, so let's blow it up a little bit here, make it a little zoomed in. We're just passing in some arguments to Matplotlib. Boom, now we can see what it looks like here. It's the first frame of the video. Yeah, it's actually sort of legible. Now, next step, though, is we need to rotate this so we can actually follow along on what we're doing with algorithms, because it's not really fun to go like this as you're creating algorithms. It might hurt your neck. And yeah, so we're going to standardize everything as part of our pre-processing. Also, this is just a helper function to plot things bigger, so I don't have to keep writing that same code you saw earlier with the fig size. Here we go. CV2 has a nice rotate function, and you just rotate 90 counterclockwise is how we want it to go here. So that's been rotated. I've just done it for one frame to test out how the code works, and I'm just using my draw frame function that I created in the cell above. Next up, let's rotate all of our pages. Nice to see, everything the same way. All right, so to simplify what we're doing, we're gonna convert the image into a black and white image. So first we'll convert it to grayscale, since we don't care about color. And then from grayscale, we're going to change that to black and white, so it makes our algorithms a little bit simpler. Because you know, having grayscale, you have to do things you know, with pixel intensity from like, you know, some number to some other number. It can be half gray, it can be fully dark. That's what grayscale really is. Binarizing it will kind of help there, making that a little bit simpler. We'll just have zeros and ones to pass around and analyze. But totally, if you're trying to do this yourself, using grayscale could be a good idea. There are some interesting things where if you apply like standard blurring or sort of standard noise profile to what you're doing, a lot of things can cancel out, and it might work better actually in grayscale. But when I was testing things out, black and white worked much better for me, so that's why we're using black and white here. Also, just because we're turning things to black and white, that doesn't mean we have to use that for OCR. We're just sort of manipulating these images to find indexes of where things happen. So we're finding page turns, and then the index is sort of the best looking page. Once we have that, we'll just pass in the grayscale because that's a better quality image for OCR purposes. So just be aware of that. You can take images, manipulate them however you want, and use that for an algorithm, but it doesn't mean that's how you're going to use them in the final output step. Here we go. This is a little bit of a harder to read list comprehension, but it's doing the grayscaling and then the thresholding to make it a binarized black and white image. Okay, so one good way to detect motion is, did anything change? And what I'm showing you here is how we can look at the difference between two images. So all we're doing is saying matrix A is frame I, set it to 10 in this case, and here's the next frame. If we plot the difference, we can see, what's the word? We can see element-wise difference. So you know, each matrix pixel is going to be subtracted against the one before. If something moved, there should be a difference there. So that's all we're doing here. So there's the difference. And I'm just going to sum everything up. So if we look at a sum of differences, theoretically, if I take, let's see if I can show you this page. Okay. So you take a page and you move it, things should be moving. You should have a non-zero value in the differences. Where the movement is smallest is probably the best spot to say this is a stationary image. So that's, you know, motion detection. And here I'm just going to plot the sum difference, where each sum is one frame to the next. So see, I'm doing A minus B, and then by zipping, you can sort of iterate through things together one step at a time. All right, so sum diffs, we're going to plot that, see what it looks like. All right, so kind of interesting here. One thing to notice is this doesn't look very good. I counted the videos, and I believe there's 3 or 4 page turns. I don't see a signal. I think I should see a signal, and that led me to believe something was wrong. I wanted to sort of show you this because it's a very common issue when working with like NumPy and different algorithms. And it's kind of some more low-level CS that you might not be aware of if you're a self-taught programmer. So what's happening here is, notice there's no value less than 0 in any of these. And why is that? The issue is because the data type that NumPy is using. So I just went to a diff.dtype and I see it's a uint8. What that means is it's unsigned. So an unsigned integer can never be negative. It's only going to be 8 bits. That's 2 to the 8 minus 1 is sort of the range. So it'll go from 0 to 2 to the 8 minus 1. And that's an unsigned integer. Now, if we wanted to do a signed 8-bit integer, that could represent numbers from 2 to the 7. From that. So by signing, you sort of lose 1 power of 2 in showing things. And all of our images are encoded in a way where it has 0 to 255 in the value spot. So we need to sort of add extra space for the computer to do its computation, because it's sort of truncating values at 0, doing some funky stuff. So all we're going to do is cast the variable. We're going to do a.asType 16 and this is an int, so it's signed int by sort of implicitly saying int means signed, uint means unsigned. And then that way we're going to get some values a little bit different here. So there we go, we see some differences. And if I plot this again, you can sort of cheat and look ahead, but take a peek. Just scrolling up here, 1 sec. Okay. So here we go. Now we see some very sharp signals. Before this was sort of truncated, but now it's clear that something happened big around the 146th frame or so, and that's presumably a page turn, because what's the biggest thing that happened in that video? It's kind of a boring video for a computer. It's the page turning. So my first sort of hypothesis is to say anything below this strong line is a page turn. I did that. Yeah, so you could just sort of write when this happens, find the best point in between the two, and that's sort of the page turn. But when I was doing this, I didn't really like it because it turns out there's an earlier page turn in the video over here, and it was missed by this algorithm. So instead of doing a sum of differences, we're going to do a cumulative sum. So we're going to look at the sum including all prior sums, if that makes sense. So it'll be sort of like a net change from a prior point. Yeah, this is the cumulative sum data. Numpy.com sum is how you do that. And it'll do, the sum of the first 2 frames differences, then the next set, then the next set, and the next set. So it's sort of like a rolling total. And when we plot this, we get a much better looking signature. See here, I see about 4 page turns about, something like that. Big sharp declines, and then the incline here. So one of those looks like a better signal. I kind of prefer it to this. It looks definitely looks better to me. So I'm going to go ahead and try out the next step. So once we find a page turn, I want to find the in-between pages. Also, it doesn't matter much if we find too many page turns, because we'll just send those to OCR, and if the values are close enough, we can sort of deduplicate things. So it's better to overestimate page turns than underestimate and miss a page turn in processing this video. Okay. So now we're going to look for the local mins. So I'm going to say each local min less than a certain value is probably a page turn, and that's the algorithm here. And a local minimum is, let's say we're looking at the local minimum between where my mouse is here and here. It's the smallest point between those 2 points. So that would be this value here. Now the local minimum between 100 and 200 would be this value here. And then the absolute minimum, the biggest one, that's the smallest, is over here. So we're just creating a function to find, given a set of points, find me the smallest value. And we're going to call that our page turns. So here we go. Created my get local mins function. I found this, I believe, on Stack Overflow. I'm actually using SciPy too, but it finds the smallest value within a given window size. That's 156 is one of them. Next one is 244. The other thing to note, just the less than. So it's less than this pixel intensity. Now, if you're doing your own video here, change the intensity values based on what you see. I was recording on an old iPhone 7. So, if you have more pixels or less pixels, you're going to need different values. It's not, pixels do matter for these type of computations. All right. Now let's plot the page turns, or what we presume are the page turns. So here's the first page. Here's the second page. There's my hand there floating around. Clearly I'm in the act of page turning. And there's another one. So to me, that looks great. It looks like I found 3 page turns. Notice I did precede the first page with a page turn by just sort of adding the first frame is a good one. And if you're recording your video yourself, just try to make sure you're when you edit things, or not that the first page looks relatively good. You're not like weirdly doing something with the book title or something at the time. Just have it open to the first page. All right, so we found the page turns. Next step is to find a stable point. So by stable, I mean find me the point that really doesn't have a lot of change surrounding it. And with that, we can use that image for OCR. Okay, so this is my helper function to find series within the page turns. We're gonna, have a series for the 0th frame to the 156, and then the next step is to find like the most stable point in there. We're also going to be using this operation called convolution. I graduated with an electrical engineering degree. I took a couple classes on this stuff. I'm pretty rusty, and I apologize I'm not the best at explaining it, but I would recommend learning more about digital signal processing if you're interested in this. There's a lot of cool stuff and complicated stuff too at times with that, and analyzing signals like what we have here. So what we're going to do is we're going to basically take a set of 30 pixels across, and we're going to add up the intensity values from our series. So what I mean by that is if the convolution is looking relatively, relatively stable. So there's, if I were to say add up the 30 adjacent values, and that seems pretty constant, like it does in this waveform here, this signal, it's probably a stationary picture. Where it moves a lot is where that sort of 30 wide adding is getting some values where the page is turning. So just sort of think of it as like a sliding rectangle of adding things. And once the page turns or the signal gets high, it's going to sort of clip and start getting influenced by that. And you can see that sort of happen here very rapidly. It's catching a clip and going up. So yeah, so we're convolving this. Also notice we're using the sum differences, not the cumulative sum differences. That's just because of the way the sort of rates of change work. It's better to use sum differences, because otherwise you'd have to take a derivative of one to get the other and all that. So here we go, drawing the frames. And there are easy derivative functions in SciPy you could use, but it's easier to use this form than the other one, this sort of integrated form. And yeah, so here's my waveform. So you can see there's clearly a stable signal here between like 40 or 50 and let's say 120, maybe even 110. Here's my candidate OCR image. To me, that looks great. Here's the next waveform. Again, sort of a similar thing. We do have some negative values, but we did find a pretty stable region. So boom, there it is. Also notice, I worked a lot with OCR, and a lot of OCR algorithms were created doing exactly what we're doing here. So they should be pretty well suited to books. There is a little curvature, there is some angling. I'm not too concerned about that, because I know that's a very common training set for OCR algorithms. They'll even use what we're going to use later, that Project Gutenberg, to train things, because it's a great set of words to compare your OCR against. So yeah, that's sort of how I'm deciding this image is okay or not. There's a little bit of tolerance on things. You don't have to smooth it out perfectly. Although that doesn't hurt, that certainly helps. Here's another one. Found another stable point here, and probably pick this one, I believe, or somewhere here. The image looks good, so at the end of the day, I just care that it found the 3 sets of pages that were good, and notice we're finding sort of the minimum in the convolution too. All right. So yeah, that's how you find pages. A little complicated. I did get something that works. There's a lot of theory here. I need to even brush up on quite a lot. So it was more of a pragmatic first attempt to get this working. The best part about our problem set is we do have training data. We do have the ability to get lots of pages quickly. So we don't have to be that concerned about things being perfect at this stage. It's better to sort of get our core building blocks out there, then improve the worst ones over time. But our problem was composed of video, extracting frames, doing OCR, and then generating audio. So sort of pick one of those four to improve on if the output isn't good. But if the output is good enough, it's really not worth it to over finesse on one piece, because small typos won't sound terrible with audio, because your brain picks up some of the gaps. And you can also sort of spell check and do grammar checks too. Anyways, this is somewhat boilerplate code to create a directory to save the pages in, and we'll use that in the next video. So here I'm doing IamWrite PNGs into this pages folder. And we'll pull that up real quick. Pages, lots of stuff here, but here's the 0th page. Notice this is the colored image. This is not the grayscale. Figured it'd be better to use the full information at first, and then we can transform it later if we want to simplify the OCR task. All right, well, thanks for watching. Hope you stay tuned for the next video and get to making your own audiobooks. Let me know if you run into any issues. It may be worthwhile for me to delve more into digital signal processing myself and create some tutorials there, or point you to some educational resources that are good. Wikipedia is not a bad source either to sort of Google. But anyways, thanks for watching.